So today we are going to begin on the network models shortest path problems, right. So shortest path problems are everywhere, and you can see that you can get such problems in road networks, in communication networks, in different sort of graphs. The essential idea is that if we have a network, then what is the shortest possible path from one node to another node. And you can see it is not always the path has to mean the path alone. Supposing we have a network, and you have to transfer some material from, let us say, one point to another point, right. And what is the minimum possible cost? In this case the path here basically is represented by cost. So, we are not really taking distance as a weight, but we take the cost as a weight. So, cost, if you just replace distance by cost, then that particular path which is the shortest path would then represent the path with the least cost, right. So, these kind of problems, therefore, shortest path problems are available in the literature in a large number, and the essential idea that how do we solve this problem. So, there are different kinds of shortest path problems, algorithms they are available. Something, the most popular one is known as the Dijkstra's algorithm. It is a algorithm for a single source shortest path problem. There are certain situations where there are negative costs or negative distances. You may be thinking that how we can have negative distances or negative costs. Particularly in when it comes to cost, sometimes what happens that if you go from a point A to point B, let us say you are going by you are carrying your material by a truck, and the truck is half full. So, the remaining half you can give on hire to other carriers, and you can charge some money, and suppose this charge is more than your original costs, then you make a net profit rather than there is a cost for going through this path. So, in that sense for that particular point A to point B, the cost could be considered as negative. So, what happens that Dijkstra's algorithm does not work if any of the distances are negative, right. For then there is a separate algorithm, you can call it the Bellman algorithm. There are other kind of algorithm like A star search algorithm. These algorithms depend on heuristics, the certain rules through which the search is sped up. So, kind of random search technique. So, we are not going to discuss such kind of algorithms, but we shall discuss the last one, that is called the Floyd's or Floyd-Warshall algorithm. Essential idea is to find out the shortest path from all pairs of the nodes. So, not just from A to B, but from A to B, A to C, A to D, B to C, and all such combinations we can find shortest path through the Floyd's algorithm. It is a matrix based approach, right. Now, you see the Dijkstra's algorithm, which will be our main topic, essentially depends on a particular principle that is called dynamic programming, right. What is dynamic programming? Dynamic programming is a method by which you can solve optimization problems such as scheduling, string editing, packaging, inventory management, and so on. The essential idea is that we have the total problem, break it into sub problems, right, and through the sub problems use an optimality principle. What is that optimality principle? We are going to discuss next, and through that optimality principle if you apply in a judicious manner, you can solve a large problem with the help of several such sub problems. So, there is a principle which is known as the Bellmans Principle of Optimality. What is Bellmans Principle of Optimality? Let us read it first. An optimal policy has the property that whatever the initial state and initial decisions are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. So, what is exactly being said here? Let us look at the diagram. So, supposing we have this network, and in this network we need to find out the shortest path from A to G. So, we start at A and we move to G. These are different costs in different paths or distances. Question is that how do you find out the A to G, right? Now, you can divide it into different sub problems. So, let us say that suppose we have already reached F. Question is how did we reach F? Let us not question that at this point of time. Having reached F, irrespective of how we have reached F, we have to now find an optimal path from F to G. So, the question is that if F is within the optimal path, you see F need not be within the optimal path, but assuming that F is an optimal path, right? Question is having reached F, what is the optimal way to reach G? It has to be found out. That is what Bellmans Principle says, right? Read once again. An optimal policy has the property that whatever the initial state and decisions are, remaining decisions must constitute an optimal policy. So, having reached F, we should optimally reach G, right? Now, let us invert the problem. You see, we have to go from A to G and we have reached F already. Instead of starting from A, let us start from G. The problem remains the same. We have to move from A to G and we have reached F, that was what we said earlier. But now, same problem, we have to go from A to G and let us begin at G. You see, from G you can reach 2 points, E and F. Is it all right? So, out of E and F, you see the distances 7 and 6. So, it is very clear that E is nearer to G and E is a more what is called promising candidate for finding the optimal path. So, let us say we choose G and we choose E, right? That means E is the nearest point if you are going to reach G. Now, you see G to E, the optimal decision is therefore 6. It does not mean that overall optimal path A to G will also have G to E. It does not mean that. It only means that if you have to go from G to E, then that distance should be 6. Now, let us look at another problem, that if we have to reach from D to G, you see if you have to reach from D to G, then from D to G the if E is involved, then from E to G we can just have 6, nothing else, and E is already optimal point as far as G is concerned. Now, out of all the several paths that we can have from D to E, you take all possible paths. If 5 is the minimum, then we have reason to believe that from E to D, right, being 5, G to D you can optimally reach at 11 total cost or total distance. So, this is the basic idea how we actually look into Bellmans Principle of Optimality. Is it all right? So, we start from a node, in this case the destination node called G, make it say permanent, and then look at the most optimal nearby point, make it permanent also. So, from the permanent that we have made, that is E, try to find out the next point which is nearer to E. So, look at F. From G to F distance is 7. So, the current level of F is 7, but we cannot reach by any other path to F, right, at a distance which is the lower than 7. So, the question is that what is the other point which has got a value less than 7? If there are none, then we can make F permanent. Anyhow, more of this as we discuss. So, let us look at one more problem and understand how this Bellmans principle has originally been devised. So, in the days when there was gold rush and people in US, they all were trying to go through unsettled country, and let us say from Missouri to California, and the idea was that what should be the stagecoach route. So, what was done, in a prudent way, it was decided that we go to the safest route should be found out by the cheapest total life insurance policy. So, what should be that minimum cost path as we reach from Missouri to California using stagecoach. So, it was an original problem through which Bellman has actually founded the optimality this principle, right. So, now let us look at the stagecoach problem. The cities are divided into 4 stages. A is the starting city, then B, C, D they are stage 1 cities, E, F, G stage 2 cities, and H and I they are stage 3 cities. And how is the thing that looks? This is how it looks, right. We have to go from A to J. Now, how do we use Bellman's principle here? How do we use? Very clear that if we have to reach from A to J, and having reached let us say H, how do we reach J? Now, from H there are several paths, right. You can go by F to I to J or H to J directly. So, what is the optimal possible path from H to J? That is 3 only, and 3 is the least distance from H to J out of all the points which you can go from a point to J. In other words, from J to H is 3, J to I is 4, J to E is say let us say 4, J to G is 7, J to F is let us say 7, etc. 3 is the lowest. So, H is the least distance point from J. So, in that sense we take J and H as our reference points and try to explore the rest of the network. How? Let us see, we will see very soon in Dijkstra's algorithm, which actually uses the Bellman's principle. So, will the shortest path of the network be the optimal solution? Yeah, how do you know that that is going to be optimal, right. Now, let us look at a particular shortest path problem, right. So, we will do parallelly also. Let us see how this problem unfolds. So, let us say we have 5 nodes P, Q, R, S and T. So, this is a shortest path problem to be solved by Dijkstra's algorithm, right. So, from P to T we are moving, and distances are like this. P to Q is 20, P to R is 25, Q to R is 17, Q to S is 30, Q to T is 42, R to T is 27 and S to T is 15. So, if you start from P, you see how we do. Initially we assign certain levels to these nodes. So, these are our 5 nodes, call it nodes, and here we put some labels, right. What are these labels? At initially we put 0 to the starting point, this is the starting point, this is the ending point, and we put these labels. That means initially P to P distance is 0 and P to other points the distances are infinity. So, that is where we begin at this level, and since the P is the starting point and this distance is 0, so we make it permanent, So, look at the slide now, exactly that is what we have done, make P permanent, because P is the least distance point from P itself. So, we highlight this particular value, the label, to 0 and P is permanent, and these are the nodes which have been made permanent, means the distance from these nodes to has already been finalized, right. After P is made permanent, you see now for every point we are, you see this is one round is done. So, we simply write P for permanent. Now, at the second round we see that out of the remaining 4 points, what are some labels that we can now modify. So, label for Q will be now minimum of the current level, that is infinity, and the level of the last permanent mode, right. What is that? LP plus DPI, right. So, you see LP is the last permanent node, level of last permanent node plus the distance from P to this point. So, this would be minimum of infinity and 0 plus 20. So, this will be 20. What is the level for R? This will be again minimum of infinity, that is the current one, and 0 plus distance, that is 25. Why 0? Because that is the level of the last permanent node. So, if I do that, then I get a value of 25. So, at the next round we recompute the levels as 0, anyway this is already available, 20, 25, infinity, right. So, that is the next level at which we compute the levels. Now, you see P, this was the last node made permanent. So, this is already permanent. Now, which one should be made permanent? Now, you see we have 20, 25, infinity and infinity as levels. The minimum amongst them should be made permanent. What does it mean? It means from P to Q the least distance will be 20, right. It does not mean any other thing. So, only the permanent nodes will be available for us to understand. So, now Q is made permanent, right? Why? Because it is the minimum, and made permanent from, that also let us note. So, this is made permanent from P, this is also made permanent from P, right. So, made permanent from is also noted. So, we have made P as permanent and also Q as permanent. So, these two nodes are made permanent. So, they are highlighted. So, look at the slides now. See, these calculations are again shown for you, that P was permanent. We compute the levels or the values for Q and R. For node Q, maximum of infinity and 0 plus 20, that is 20, the infinity and 0 plus 25, that is 25, and these values are obtained, and now P is the last permanent node, all right. So, that last permanent node values are taken here, those distance is added, and the minimum of those, sorry, this is not max, that should be minimum, and minimum of that is computed, all right. So, now Q is made permanent, and list of permanent nodes are now P and Q. Now, after that, after we have found that is P and Q as permanent, so once again Q is the last permanent node, all right. So, we are here. So, let us recompute those levels once again. So, if you recompute those levels once again, what should be our next levels? The next levels from Q, you see distance is there for R and S, no distance is there for T, is it all right? So, you see what would be the new level for R? See, this is already done, this is at say this is round 1, this is round 2. So, all these are round 2 calculations. Now, we are at round 3. So, round 3, what will be the level of R? It should be minimum of current level, that is 20, 25, that is the level now, and 20 plus, that is the last node to be made permanent, plus 17. So, it should be, now which one is minimum out of 25 and 37? It should be 25 itself. So, no change happens as far as level of R is concerned. What about level of S? Level of S will now become minimum of, current level of S is infinity, and Q, that is last node, it should be 20 plus 30. So, it should be 50. And can we calculate T? T also we can calculate. Level of T, that should be minimum of infinity and 20 plus 42. So, 62. So, we have already computed all these levels. So, 0, 20, 25, 50 and 62. So, which one is the minimum? You see these two are already made permanent. So, you see these two are, we need not worry, because they are already made permanent and made permanent from P, and 25 is also made from P, they are all made from P now. Now, 50 is, sorry, 50 is made from Q, and these are also Q. So, which one should be made permanent? 25, because this is the least. So, now this is the last node to have made permanent. All right. So, now look at this slide once again. So, P and Q were permanent, and we calculate all these values. Q is the last permanent node, and here we made R also as permanent. So, as we made R as permanent and these are the values, 25, 50 and 62, right. Now, once you make R permanent, this is the level 3. Now, we come to next level, that is level 4. So, we have to take the distances from R. So, what are the levels? Now, levels are 0, 20, 25, no change here. Can you change 50 S, because no path from R to S. So, R to S no path, no direct path. So, obviously no change happens in S. What about T? At this level, that is at the 4th round, you know, LT equal to minimum of current level 62, last node to have made permanent is R is also made permanent. So, 62 plus 25, that is the last node level R, that is 25, and the distance, that is 27. So, which one is minimum out of 62 and 25 and 27? It becomes 52. So, now we have LT coming out to be 52. So, now which one should be made permanent? Very clear. Then we have to make, now 50 is lower. So, that should be made permanent. So, S is now made permanent, and last node to have made permanent is this. So, we have done level 4. Now, let us look at this also, see this computation, and here you know S is now also made permanent, and these are the 50 and 52. So, S is now permanent. So, now we come to the 5th level. Let us say what are the levels now? The levels are 0, 20, 25 and 50. So, only thing we can now compute LT once again, because what is the last node to have made permanent? S. It should be minimum of your current value 52 and comma, then last node to have made permanent 50 plus that distance, that is 15, 15. So, out of 52 and 65, which one is minimum? 52. So, no changes. So, we have 52 itself, and since all other nodes are now permanent, so now T is also made permanent, right. So, T is permanent, and then our problem is solved, and we have now look here, then this is made permanent from R, right. 50, this is made permanent from Q, 25 is made permanent from P, this is from P, this is from P. So, shortest path if you have to find, then you have to see T is made permanent from R. So, we write T here and then write R. R is made permanent from P. So, that is all. So, this is the shortest path. So, you see, so made permanent from P, 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 Q, R, these are going to give us an idea of what is the shortest path, the P, R, T. And what is the shortest path, you know, distance? It is 52. So, look at this 52, fine. So, that is about how we use Dijkstra's algorithm to solve shortest path problem, right. We will do one more problem, but currently we stop here and see this is our final solution, that T is made permanent from R, R is made permanent from P. So, shortest path is P R T and length is 52, right. So, thank you very much.